Okay, so I guess we can start. It's past 4 Central European Time. So hello everyone, my name is Marcin Kubacki. I'm Chief Software Architect at Storware. And today we are going to discuss persistent volumes with Brian from Catalogic. So Brian, the stage is yours.
Thank you, Marcin. How are you? We're going to first run through a few slides here. First of all, my name is Brian Sietsma. I am the solutions architect at Catalogic Software. We are a partner with Storware over here in the United States. What we're going to be spending time talking about today, most of the time spending specifically on talking about persistent volumes and persistent volume claims and how they are used in Kubernetes environments. We'll also spend a little bit of time discussing how we protect that data in those persistent volumes. We'll first go through a few slides and then we'll walk through some demonstration as well. So I'm sure I'm not the only one, but I still have that recurring dream where I am halfway through an essay or a thesis for school or for university, and without warning, the screen goes black. My paper's gone, I have not saved my changes, and then I wake up in a cold sweat, realizing I'm way past school. But similarly, for those of you that maybe play video games, you all know that the first thing that you do when you defeat a hard level or complete a difficult task is that you save the game, you save your progress. Now, if you're this concerned about saving your progress in a video game, I'm sure you've taken considerable time thinking about how you're protecting your organization's persistent data. That's where Kubernetes and persistent volumes come in. So what is persistent data? Persistent data is non-transient, business critical information. This type of data, really more than anything, needs robust and durable storage to make sure that this data is never at risk, is always available to users and applications. Now, this can be accomplished, like I said, within a Kubernetes environment using persistent volumes. So what is a persistent volume and how is it different than a regular volume? So a persistent volume is one of two storage abstracts that are available in Kubernetes. You have your typical volumes and you have persistent volumes. With a typical Kubernetes volume, the volume only exists while the pod that contains the volume also exists. This means that once the pod is deleted, the associated volume is also deleted. With a persistent volume, on the other hand, this remains available outside of the pod's lifecycle. So if the containing pod is deleted, the persistent volume remains, and that can be made available to claim by another pod if that's required. So all the while retaining the data on that persistent volume.
Great, Brian. And what types of storage can be used, for instance, to store this data?
Good question. So persistent volume types are implemented as plugins. Kubernetes currently supports a wide range of plugins. This can be NFS, this can be iSCSI, vSphere volumes, GlusterFS, OpenStack storage. So there's a large variety of different persistent volume types that can be used in Kubernetes. Make sense? So really, long story short, when it comes to talking about persistent volumes, if the data stored in the pods is temporary data and doesn't need to be retained regardless of the pod's lifecycle, maybe a typical Kubernetes volume may be fine. But if the data is persistent data, it needs to be retained even after the pod has been deleted. A persistent volume would be a much better choice. So you may be wondering then, how are persistent volumes used in Kubernetes? And that's what we're going to be spending the rest of the slides on here. When it comes to creating or managing those persistent volumes, an administrator or a storage class will create a persistent volume by provisioning some dedicated storage. And that, like I just mentioned, can be any of those different types of volumes. Once the persistent volume is created, it can be claimed by a persistent volume claim. This is essentially a request by storage or for storage by a user or developer that can then be used to store data for pods, applications, things like that. So a persistent volume claim describes the amount and characteristics of the storage that's required, and then it goes out and finds a persistent volume that matches that criteria. And it claims that volume, or it claims that persistent volume, and it binds to that. So when it comes to provisioning a persistent volume, there's really two options. There's static and there's dynamic. So what's the difference? With a static provisioned persistent volume, a cluster administrator creates a number of persistent volumes. They carry the details of the real storage, which is available for use by the cluster users. When it comes to the claim, it will point directly to a specific persistent volume. For a dynamic provisioning, this is used when really none of the available persistent volumes created by the admin match the needs for that persistent volume claim. When this is the case, the cluster will try to dynamically provision a volume for the persistent volume claim using that predefined storage class, which will be configured to allow for that dynamic provisioning. So essentially what this means is when a persistent volume claim is created with dynamic provisioning, it doesn't go out and it doesn't get pointed to a specific persistent volume, or maybe it doesn't find a persistent volume that matches the criteria. And that's where Kubernetes can then, based on the storage class, dynamically create a persistent volume that matches the criteria for the claim. So when a user creates that persistent volume claim, a control loop picks up that new claim and finds a matching persistent volume if there is one, right? In this case, one may be dynamically provisioned if that's the case, like I just mentioned. So at that point, the control loop binds the persistent volume claim to the persistent volume. So if there's no matching claim and dynamic provisioning is not configured, that persistent volume claim will sit out there looking for a persistent volume to be created that matches the specific criteria. It will sit there indefinitely until a matching persistent volume is created. Now, how would we use these persistent volumes in Kubernetes? So pods that need resources or applications that need resources use persistent volume claims like a volume. They have specific resources that are needed. The cluster then inspects the claim to find the bound persistent volume. So once that persistent volume is bound to the claim, that then gets mounted or bound to the persistent volume claim, and then it mounts that volume for the pod to use. So the persistent volume claim binds to the persistent volume that has the resources that the pod will then use for the applications and things like that. Once a user has a claim and that claim is bound, the bound persistent volume belongs to the user for as long as you need it. It's bound specifically to that persistent volume claim. When a user is done with their volume, they can choose to delete the persistent volume claim from the API, and that allows for reclamation of the resource. That persistent volume becomes available for another job, for another persistent volume claim to bind to it. All right. Now, what happens if I didn't request enough storage and need to perhaps expand the persistent volume claim? Again, like I mentioned, the persistent volume claim is a specific request for resources. So if you need to add resources to that request, Kubernetes now can support expansion of that persistent volume claim. That's now enabled by default, which means that this allow volume expansion field over on the right here is set to true by default. This is necessary in order to allow for this volume claim to be expanded. So then all you have to do is request a larger volume. You do that by editing the persistent volume claim object and specifying a larger size. This then triggers expansion of the volume that backs the underlying persistent volume. So it will automatically understand where that volume is coming from based off of the bound persistent volume, and it will expand that particular volume. it's not like a new persistent volume is created to satisfy the claim. Instead, the existing persistent volume is expanded. It's resized for those new, the new necessary size. So just to look at a few of these specific specs and status of the persistent volume here. This is what a lot of the object looks like, and there's plenty of fields in here that we'll discuss. The first is capacity. You'll notice there's a storage here. This is saying that there's 5 gigs of storage available for this persistent volume. And you'll also notice that this is being pulled from an NFS volume, and this is the particular path that is being used.
Brian, and how, let's say, this storage is being allocated?
Good question. So using any of the volume options that I mentioned earlier, unless it's otherwise provisioned dynamically, Kubernetes will choose from a list of available storage that matches the needs for the persistent volume. So you can see here that this particular persistent volume is using NFS as the storage, as the volume. But this can be any storage underneath that. This can be any block storage that's carved out, pointed to that NFS share, and then again providing that mount point, the path where that storage is provisioned. So that's how we would allocate storage for a persistent volume. Some of the other fields on here, including the volume mode, this can be either block or file system. You'll notice this is it's file system in this case. Access modes, this will show you what access modes are supported by the resource provider. So this one in particular is read, write, once. Also, a persistent volume can have a specific storage class. I mentioned this a bit earlier when we were talking about dynamic provisioning. You can set a specific storage class, which basically says this persistent volume can only be bound to persistent volume claims that request that particular class. A persistent volume with no storage class name has no class, and it can be bound to any persistent volume claim that doesn't request a particular class. So if it needs to be pointed to a particular storage class, in this case, it's just the storage class name is slow. So if a persistent volume claim is pointed to this slow storage class, it's going to look for persistent volumes that are also in that same storage class. Now, persistent volume claims, these are some of the similar fields that are available when provisioning or creating a persistent volume claim. Again, access and volume modes are very similar to the persistent volume. They show the either block or file system, and let's see, what was the other one? Access mode, again, read, write, once. Resources, on the other hand, here shows the specific request for quantities of a resource. So again, the persistent volume claim is requesting specific resources. This is where that request comes in. It's then going to look for a persistent volume that has these requested resources. The selector, this next field down here, shows the claim can specify a label selector. Really, what this does is it further filters the set of volumes. Only persistent volumes whose labels match the selector can be bound to the claim, a bit similar to the storage class. This will group the persistent volume into a specific label, and the persistent volume claim can use that label to point to those particular persistent volumes. And then finally, storage class. A claim can request a class, just like the other direction with a persistent volume. The claim can request a storage class by specifying or request a class by specifying a storage class, which will point only to persistent volumes that share that same storage class. All right. So that is all the slides I have. The next thing that we're going to do is walk through a quick demonstration of what this looks like in a Kubernetes UI. Go ahead and create some persistent volumes and some persistent volume claims. and let you take a look at what that looks like live.
Okay.
So what I'm going to do,
you need to unshare so I could share my screen.
Yeah.
Okay, and at the same time, I think we have received a question on the chat, so it was related. So how do we identify storage types supported? So I have already opened here documentation. Basically, there is a tons of supported types of persistent volumes out there. Some of them are file systems, basically. Some of them are basically a block storage. So you can choose whatever you like. And later you have storage classes, which correspond to these that are already configured in your environment. So later you have ability to choose between fast or slow storage classes, and behind the scenes there will be appropriate backend in this case. Okay, so let's continue. Brian, so you should now be able to control this environment.
Perfect. Thank you. Yeah, so this is the Kubernetes UI. What we're going to do first is go up here and we're going to create a persistent volume. So this, what we do is we'll just copy, let me copy and paste this from my end. This is just copying, pasting a YAML file for this. Let's see if it's going to work here.
Okay, if not, let me just copy it from here. So we have prepared. We need to, for a moment, leave the mouse. Okay, so first let's start with regular volume, right?
Yes, yes. So this is a regular persistent volume. Again, you'll see some of those fields that we discussed earlier. What I'm going to do is I need to specify a specific volume that we're creating here. So let me just make sure we're not overwriting anything. So again, what this is going to do is go ahead and create that persistent volume based on the information provided. And again, this is very similar to what we were just looking at, right? This is a specific persistent volume that has 1 gig of storage attached to it. It's using NFS as the volume type. And I'm going to go ahead and upload this. You'll see that this will get created under the persistent volumes section here. This is that new persistent volume that we created. Now, the next thing that we're going to do is then create a dynamic persistent volume claim. And Marcin, if you want to copy, paste that YAML file in here for me, that would be helpful.
Yep, already there.
Perfect. So again, this is going to be creating a dynamic persistent volume or claim, persistent volume claim. This is looking to dynamically provision this. And you'll see the storage class is going to point that to the NFS dynamic provisioning storage class. So go ahead and we'll upload this as well. This will take a second, but we'll look down here to the persistent volume claims section here. And you'll notice that this has been dynamically bound to the this particular persistent volume based off of the requested resources for that persistent volume claim. All right, so that was a dynamic provisioned persistent volume claim. The next thing we're going to do is one with that is statically provisioned.
Okay.
So this will look similar as well. There will be a few changes here that you'll notice. This is not going to be pointing to a specific storage class. This is being pointed to a particular volume. So this is why it's or how it's being statically provisioned. So again, I'll upload this particular persistent volume claim, and we'll jump back down to this section here. And again, you'll notice that this has been statically provisioned and will be bound to the volume that we pointed the claim to. So again, that volume or the volume restored to. All right. And the last thing that I just want to quickly show you in here is how we will go ahead and create a deployment. So Marcin, if you can paste that in here.
Notice that this actually, there are two YAML files in here. So we are creating claim and deployment at the same time. And in this deployment, we are actually referring to that claim.
Yes, exactly, exactly.
So here you can notice that I have a claim name. I have specified the one that is already here allocated. Okay, so let's hit upload then.
Yep, and then you'll notice that if we head to deployments here, you'll see that new deployment was created. And if we go down to the persistent volumes claim, it will create the persistent volume claim that was referred to in that particular deployment. All right, so Marcin, I think that's everything I wanted to show here.
Okay, so
I'll pass it back to you.
Yeah, brief overview of that question. We tend to receive also questions about the data protection, because some people think that it may not be really necessary to protect such persistent volume. So any sort of persistence basically requires also you to protect that volumes. So you have to keep in mind that underneath there is some sort of storage, and it can just basically disappear someday. Regardless if it's block storage or if it's something else, you have to be aware that it's not always about even losing the underneath infrastructure, but also you can just basically damage data by yourself. So you would like sometimes to revert back to this particular one. And approach with Kubernetes environment is slightly different. It's not like in regular virtualization that basically you assume that everything is stateful and you have option to snapshot volumes, for instance. This sort of capability is being still developed in Kubernetes world, and especially that depending on the environment, depending on the storage that you are using, you may have that capability or not. Now, one way to basically protect your persistent volume is just basically go directly to your storage, right? So if you have, let's say, some sort of disk array behind the scenes, basically you copy data from there. And there you may have actually some sort of snapshot capability at this point. Then you have some options to copy data as the pods are running. And now this is a tricky part, because technically you may find it inconsistent. I mean, if you are copying data as it is being modified, you may end up with inconsistent backup, basically. So let's say it's good for something very basic, like, well, configuration. It's not the thing that you may want to have in persistent volumes. You probably want to have something that really keeps your state of your application, not the configuration, right? Because with the Kubernetes approach, we are supposed to build applications that they don't have some sort of strange configuration which is not as a part of the template of the provisioning template. So it should be basically outside. But we see also tendency that there are some solutions that install some sort of the agents or within the pod, or pods are being deployed as the part of the deployment, and this additional pod basically tries to grab data from the persistent volumes that you have seen that have been created during this deployment, for instance, right? So the data is being copied, but still it is not that level of the consistency. You have to be aware of that. Now, well, we have vprotect that basically supports Kubernetes, and let me show one thing here. You have probably noticed that there was Nginx deployment, this one, and we see that it has some PV already assigned. So there is one claim available in there. And the idea behind this is to have a single solution that basically allows you to cover all of the persistent volumes in your Kubernetes, regardless of some sort of additional work needed to find appropriate volume on your real storage. So here from the vProtect, you basically have these additional volumes. You see them here, and you treat all of the deployments still as, let's say, environment. So you think you know exactly what type of data, which volumes need to be actually protected and which not. So this is one step that you don't really have to identify them on your own and later somehow grab this NFS folder behind the scenes and copy it or whatever, right? So this is being done automatically. Now, when you are restoring here, you have option to override config. So by default, obviously, vProtect is going to use the dynamic allocation in that matter, but here you see the same spec that you have probably noticed already, and you provide storage class name and volume name as well. So you may basically create earlier a new volume specifically for that restored machine. Well, let's say not machine, but because we are talking about the deployment, and vProtect is going to pass it later to the Kubernetes to use this particular volume instead of allocating it according to the requirements as you can see. So you have option to back up some subsets of the volumes, and basically later when you're restoring, you allocate it maybe maybe yourself. That's one way to go, or maybe with the dynamic provisioning, as you have noticed earlier. The claim itself would ask behind the scenes to allocate new storage for that matter. This dynamic allocation obviously needs to be supported. So there are tons of providers available for Kubernetes, and not all of them are, first of all, compatible, but even if they are, they may not be able to provision storage for you. So this is one of the things that you need to be aware during such operations. Okay, so let me just verify if there are some additional questions. Data at rest encryption is available in persistence volume using KMS. Don't think it is available for all of the providers. And I assume that even if you have such provider, then it probably would be configurable on the other side. Not like, think about it like this. Volume basically behind the scenes is being provisioned using, well, basically file system is being created on top of it. There is just a short list of file systems that are being initialized on top of these block storage that you have allocated. Now, XFS, X4, and something else was on that list. These don't provide you any native encryption at that point. So this is like layer up on top of something that would provide you some sort of mechanism for such encryption. So I don't believe this would be available. The other option would be probably to attach a block device, because the other option is to allow claims to be not file system based, I mean not mount it as a file system, but rather give you a block device. And technically, from now on, you could do everything what you need to do, right? So you could initialize and try to encrypt it, maybe from the container level, if it's available on the kernel side as well. Okay, I don't see any additional questions. If you'd like to ask anything else, you can also unmute yourself. Okay, so this session is going to be also shared on some social media, so you will have ability to check out again what we have been talking about here today. Thank you, Brian. Thank you, everyone, for joining this session as well, and stay tuned.
Thanks, everyone. Thanks, Marcin.